You can hear me? And you can see my slides?
Yep, sure can.
Okay, thank you very much. So I'm glad to be here today to talk to you about permafrost engineering. So I will essentially continue the work very good work done by Simon 2 weeks ago. Simon has introduced heat transfer and has introduced soil mechanics of frozen, thawing, and thawed soils. And that's fundamental for permafrost engineering. So I will today discuss a little bit about geotechnical investigation, which is key to decision-making, and then also talk about different strategy for design on permafrost. Of course, it's too short a presentation to discuss about actual methodology, but we're simply going to look at the different strategy and methods that can be used and like a general approach that can be used to solve some permafrost problem. So, if I can get the slides to move. Okay, a few words about myself. So I got involved in permafrost engineering about 35 years ago. At that time, I was with the Quebec Ministry of Transportation, and we were involved in a vast airstrip and road construction program in Nunavik. So altogether, we designed and participated to the construction of, actually participated to the design and the construction of 13 airstrip and access road in Nunavik. And at that time, we didn't know much about permafrost, so we had to learn about permafrost and potential problem, and did the best we could at the time. After construction was done, a little later, I became a professor at Laval University in 1997, and most of my research work and teaching was on pavement engineering and cold region engineering. Since 2020, I'm an active retiree, probably not enough retired and too active, but still have the title of a retiree. So that's essentially where I am. So, of course, the development of northern communities and industry, as you can imagine, depends heavily on sustainable infrastructure. You see on the slide here the airstrip and the access road, which is the basic link for most community in the north. It's the only link that allow them to have year-round access to their community and to the rest of Canada. There's, of course, also some areas where there's roads. There's a couple of roads that go up north. These roads are significant engineering accomplishment in terms of the engineering work done to design those roads and to construct them on permafrost. They also bring their great deal of maintenance problem. So there's also railways. I should maybe say railway. There's actually one railway going to Churchill, perhaps one that has a little bit of permafrost issue near Cherfeville, Quebec, and maybe that railway may be extended to Kuujjuaq in the future. And finally, there's a project for a railway on Baffin Island, which is also going to be a major engineering challenge. There's, of course, bridges for water crossing of roads and railways. Structure, of course, the design of bridges is something different than the design of an embankment. And there's also buildings for administration, to support the management of these infrastructure. So permafrost is, of course, it's a fragile environment. So the permafrost, you've all heard about permafrost. in presentation 1 and 3 of the series. Of course, you've heard a great deal about how it can be a problem and how it can be unstable. So for engineers, of course, this is a foundation, and we understand that it is a foundation that can be unstable. And we understand that also the stability of that foundation depends heavily on climate stability, and also on the fact that there's undisturbed soil and surface characteristic, which is not that's not obvious to maintain when you're building something. We know also that permafrost can contain large volume of ice. You see in that example here a nice exposure of soil that's just due to a recent landslide at that location, where you can see very clearly the ice wedges, and you can see also the ice-rich soil in the layer, the deeper layer in the soil. There's about 70 to 80% of ice in that soil. So it's definitely a soil that can be a problem if something is disturbed. So what happened when the equilibrium is broken? There's, of course, there's damage to structures. Damage have been observed on all type of structure, bridges, roads, buildings in the north. And of course, for all sorts of good reason. One of them being climate change. So climate change actually is very convenient for engineers because we can blame everything on climate change, and that's simple. We also have another reason is that we have poorly adapted structure, and that again is not, we don't say it loudly, but we're not yet doing a very good job in the north in terms of designing structure to take into consideration the sensitivity of permafrost. So again, climate change and design are the two main reasons for damage that we're observing in the north. Looking at the big picture, general strategy when you're designing something. First of all, you have to know if there's permafrost. You're in the north, but in many areas in the north, there's no permafrost. If there's no permafrost, designing something is similar to what you'd be doing in the south, and you can use all the design guidelines and the codes that you find in the south. Of course, considering cold climate condition in the north. If there's permafrost, the second question is it ice rich? If it's not ice rich, then you go back to the normal design approach because there's probably not much consequence of permafrost degradation on the stability of the structure. If the permafrost is ice rich, then you need to know what's the ice content, because this will dictate the rest of the strategy. Like if we have low ice content, low excess ice content, moderate or high, would dictate what's next. So the first part of that decision chart relies essentially on the geotechnical study. You need to know what's there. You need to understand the context, and you need to understand permafrost. So a few words about site investigation. It's going to be very quick because I don't have much time altogether. So I'll just run quickly through site investigation. First slide say what's the minimal information that's required. Of course, we need soil type and physical property. So just, is it sand, is it clay, is it silt? Of course, this is fundamental for a foundation design. This, of course, is information that's easily to get in the active layer. And it probably tells a lot about the foundation of the structure. We also need to know the thickness of the active layer. The active layer would probably be the layer that is going to be have the lowest strength in the system. So you need to know how thick it is and what are the characteristics of the active layer. Thirdly, and very importantly, the spatial distribution of toss-sensitive permafrost. That means ice-rich permafrost and exposed to thawing. So if you have ice-rich permafrost at 20-meter depth, it's probably not a major concern because you probably never thawed that permafrost during the design life of your structure. So ice-rich permafrost and exposed to thawing over the design life of your structure, this is what you need to know. So first of all, you need to know that permafrost is toss sensitive. So you need also to know type of ground ice. Massive ice, segregated ice, type of segregated ice will change the behavior of the soil. So it's very important to know and understand that. You need to know the physical property of the first few meters at the top of permafrost. Again, this is extremely important because if the climate change or design cause the top of permafrost to melt, you need to know what you're going to have to deal with, what type of movement it's going to generate, what type of loss of bearing capacity you're going to get during thawing. So it's extremely important to know that. And the number of meters you need to be concerned about, this depends on the design life and the projection on climate change. So again, this is fundamental information. Finally, you need to know as much as possible on soil temperature and site-specific climate condition. Now, if you're designing in the middle of a Baffin Island, for instance, and you're relying on Iqaluit meteo station, you probably have wrong information to start with, or information does not reflect the condition in middle of Baffin Island. So when you go and do site investigation, you should always at least leave behind thermistors to measure to make some measurement of air temperature and soil temperature. And no matter if it's very short time, it's going to be helpful for modeling your system. So quality and quantity of information required during the geotechnical investigation depend a lot on the type of project and the risk involved. So that chart, that comes from the TAC design guide for transportation infrastructure on permafrost. And you have on the y-axis is failure consequence, and the x-axis is permafrost sensitivity to degradation. So of course, local unpaved roads don't have there's not a major consequence if there's a failure, while airport, you have a much higher consequence. And of course, paved road or railway would be somewhere in between there. So essentially, you need to adapt your investigation to the project. So generally, you'll need high density, high quality information when the failure consequences are high and the sensitivity of the construction to climate change is high. You need low density and minimal quality if you have low failure consequence and low sensitivity to permafrost degradation. So everything needs to be adapted. And there's guidelines to help you do that. And again, referring to the TAC guide, there's a recommended level of investigation for different classes of work. It's really minimum level recommended for each level. So again, you can refer to that. I'm not going to go through that table, but it's available in the TAC guide if you want to refer to something. So site investigation in the north is difficult. It's difficult to do good geotechnical study in the north because of the logistic of bringing equipment and do some drilling, sampling, and doing some geophysical studies. So you need to be smart when you do the investigation. You need to use a step approach. First step being to use as much as possible the information contained in an expensive data source. to identify soil type and potential sensitive area. So geological maps and reports are usually free and easy to access. Aerial photographs are cost a few bucks, but they are easy to access. Satellite imagery is again, very good source of information, and information from remote sensing. All this information is relatively inexpensive, provides lots of preliminary information on the project. Just to give you an example, this is a basic Google Earth image from a site on Baffin Island, and you can easily get lots of information on just from that image. You know, like somebody that has a good eye, a geological eye, can see that there's a moraine here. So for frontal moraine, and these are outwash deposits here. So moraine, of course, is a well-graded material. It's granular typically, but can contain a lot of silt, can be ice rich, can be frost susceptible, excuse me, and also there's a risk of finding buried ice under moraine. So it's already information that's very useful for a project. Outwash deposits are granular material, very good source of gravel if you're building, but they can also cover buried ice. So something to be worried about. You can see here the braided channel, and these type of channels indicate that there's lots of granular material in there, and it's generally good quality gravel or sand that can be used for construction. It can be a good foundation for something. You can also see that there's lots of ice wedge, probably some buried ice or under the trough of the wedge. You can also probably see that there's finer grain material here, lacustrine deposit. There's a little bit of a few features here that look like frost mound or frost mound that could indicate presence of ice. And again, if you look closely, you'll see here that not here, but here that there's a pingo being formed in a drain lake area. So just by looking very quickly at an aerial photo, in this case, a satellite image, you can get lots of very useful and helpful information on your site. Once you've put on a map all that information, you need to visit the site and confirm some information. So you need confirm observation you made on the photos, on the maps, on the geological maps. So going on the site will allow you to see visually the type of problem you can have, sign of instability, sign of ice, frost susceptible soils. You can dig shallow pits using a shovel and identify your soil, confirm soil type, and do some sampling. So again, if you're walking your site, you'll find no indication of frost-sensitive soil, like frost boils. You can see cryogenic mounds that typically indicates the presence of ice underneath. You can see also indication of buried ice, like a trough of polygons. Typically, well, that means that there's probably an ice wedge under that. Is it a big wedge or a small wedge? Something to be verified. This is the top. That picture is the top of a moraine, a frontal moraine. And you can see here a depression that, well, could be normal because these moraines are very irregular in shape. But when you see cracks in gravel that are fresh cracks, obviously there's something going on. There's something, this is settling. And if this is settling, that's because there's ice underneath. So there's buried ice under that moraine. And this, of course, is a major information, something very important information to keep in mind. Of course, indication of slope movement, soil fluctuation can cause some problem to infrastructure. The most the prevailing problem currently in the north is the active layer detachment and also toss lumps that are getting to be more and more active near infrastructure. You see here a case where there's a toss lump in natural ground near the Dempster Highway on the Northwest Territory side. And if you keep going on the road, you'll see another toss lumps in a natural environment, but two toss lumps that are actually were activated recently near the road. One that was filled back by the government of Northwest Territory, and the other one which is threatening a little bit the embankment here. So all these indications, of course, are signs of ice-rich soil, unstable soil, and potential risk for the infrastructure. The first two steps are, of course, key activity to plan the next step, which is site characterization. This usually involves some geophysical investigation and also geotechnical investigation. Geophysical methods are very helpful in helping to quantify the spatial distribution and the depth of potential problem. And the most commonly used techniques are seismic can be used for for a few, like to detect the presence of bedrock and to detect the depth of permafrost, but it's not widely used. The two widely used techniques are electrical resistivity and ground penetrating radar. And those two techniques have been used widely in the last decades to characterize permafrost, and researchers are coming with very good analysis tool for these techniques. So it's possible to detect zones of high resistivity that typically that are typical of ice-rich or massive ice, and also to detect interface with ground penetrating radar, sort of the bottom of the active layer, and also the stratigraphy in the soil. Microgravimetry can also be interesting to detect massive ice. It has been used experimentally and successfully to detect buried ice in the Yukon and also in Baffin Island. So it's something that can be also a useful technique. At the end, you need to go and drill. So you need to verify the information. You need to have some detail, some high-level detail about permafrost. So manual technique can be used for shallow test pits, but usually you don't get information about permafrost. You can use backhoe, small backhoe that can be transported around, and so you can dig through the active layer and also chip the top part of the permafrost using a jackhammer to get some information. But these techniques are rather limited. At the end, you need to use heavier technique, mechanical technique. This is a relatively lightweight drilling rig that allows you to drill in permafrost to recover samples, but it takes time to drill with that kind of machine. Or you can use the full, the powerful drilling equipment with cooling liquid to allow recuperation of frozen samples. That's probably at the end, you need to get some information using techniques like that. There's also in-situ testing that can be done. This is an example on top right of a penetrometer, static penetrometer that's used to determine the property of permafrost in the top layers. You can also use vein testing to measure shear resistance at the bottom of the active layer. Dynamic penetrometer also give you information. So these are all information available to help characterize permafrost. And the final step for high-level information is you need to bring frozen core to the laboratory. first of all, to determine physical properties, to describe the cores using visual inspection or CAT scan, so scanning the core to give information about volumetric content of ice and structure of ice and things like that. And finally, if there's a concern about mechanical behavior, you can do toss settlement consolidation test and also creep test to determine soil property. Simon has talked about those tests, so I won't come back. I will refer to that later in the design, but I won't discuss any more about those tests. Finally, soil temperature and climatic data is very important. Again, site-specific climate data is essential if you want to calibrate a model to your site. No, again, you cannot use information from hundreds of kilometers away at different altitude, different latitude, and use that information for modeling. You're going to have wrong, a model is going to be biased. So any bit of information that you get on soil temperature and air temperature, even if it's not for a full year, is going to be very useful to calibrate a model and do thermal design. So essentially, at that point, you know what you're dealing with. So assuming that you're in a condition where you have excess ice content, and you're on that point with taking care of a condition where you don't need to do special design. So when you have excess ice, well, if you have low content of excess ice, so typically a little bit above the natural porosity of the soil, so something that would look like 20 to 30% water content, that can probably be handled through slightly modified but normal design and intensive maintenance. If you have moderate ice content, so somewhere between 30 to 40 or 50% of water content, you probably should consider adaptation, but in some cases, depending on your tolerance for strain deformation, taw deformation or taw strain, you can probably deal with, in some cases, with intensive maintenance, but in other cases, you need to adapt. And finally, in cases where you have high level of excess ice, you need to adapt. Adaptation, there's three strategies for adaptation. You can either reinforce your structure or your embankment to allow it to cope with the movements. So it's possible. There's some design for building that have been proposed to so the system can actually accommodate movement of the foundation of the building. There's for some embankments, you can allow some movement to some level and reinforce the embankment so it doesn't crack or it doesn't spread or it doesn't collapse if there's a localized settlement. So that strategy is called reinforcement. You can also improve soil. The easiest way to do that would be excavate and replace taw-sensitive soil using dry granular material, for instance. You can also induce thawing and improve the quality of your foundation by imposing thawing prior to construction. We can discuss about that later. And finally, the third strategy, which has been the most widely used strategy to cope with permafrost problem, is thermal stabilization. Okay, this picture a little bit busy, but it actually illustrates the three strategy. The top picture is taw depth. So you have the active layer in the top part of the picture, and you have the top of permafrost, which we suppose is ice rich. So when you have this condition, of course, you can let things happen. So you can let permafrost degrade with time due to climate change and disturbance caused by construction. The permafrost will slowly degrade with time. And in the case where you build and maintain, do intensive maintenance, you would simply have to maintain every time the level of service is getting too low. You need to upgrade your system, so you need to rehabilitate or whatever is needed to maintain a level of service. Soil improvement, this actually illustrates induced thawing. So you force thawing into the top part of the permafrost to a level where you feel confident that in the design life of your pavement, you'll never reach back that level. And then let permafrost regrade. So the reaggraded permafrost will be typically ice poor or lower ice content. And from there, you can let the system thaw, but at that point, the consequence would be relatively low. So this is actually the bottom figure illustrate the elevation of a soil column as a function of time. So in the case you do nothing, this is the settlement that will occur, and this is what you need to compensate with intensive maintenance. If you do induced thawing, again, you will force settlement, thaw settlement of your foundation, and then there's going to be a readjustment caused by frost heaving in the regraded permafrost, in the regraded layer. And then from there, there shouldn't be any significant movement, and assume if the calculation is well made, you should have a stable condition for the design life of your structure. The third solution is to actually enhance thermal conditions, so do thermal stabilization. The easiest way to see the problem is you actually induce aggradation of the permafrost near the interface between your soil and your embankment, and preferably inside the embankment. And then that provides you a buffer so permafrost can degrade and not reach the initial level of permafrost prior to construction. So in that case, you would have stable condition during the life, the service life of the structure. So these are essentially the three strategies. I'm going to talk a little bit about embankment design. I'm not going to talk much about building a structure design because most of my experience is with embankment, but the same principle apply also to building foundation, and structures need to be adapted for the specific condition of those structures. But embankment can be adapted to permafrost degradation. So again, when you do embankment design in the north, you first thing you need to do is design for thermal stability. So the thing that's different in the north compared to the engineering work in the north and the south. In the south, they will essentially consider mechanical stability, and design is going to be made based on mechanical stability. But in the north, mechanical stability depends on thermal stability. So you first need to design for thermal stability. And if you do a good job, the mechanical stability shouldn't be a problem. But you still need to investigate and design for mechanical stability. And we're going to discuss a little bit about a few techniques that can allow you to adapt an embankment to permafrost degradation and to thermal degradation. So thermal stability, it is clear and unfortunately not always done, but it should be done. Thermal design is required if you're building on thaw-sensitive permafrost. That's, I think, it's not very responsible not to do thermal design if you're building on thaw-sensitive permafrost. There can be very important consequence of not knowing what you're doing when you're building on thaw-sensitive permafrost. So thermal design is required. And the idea is to impose favorable and long-term stable thermal condition in permafrost underneath the embankment. Thermal design needs to take into consideration the geometry of the embankment. In my old days, when I was working in Nunavik for the design of airstrips, we were only investigating the center line of the airstrip, and we're assuming that if we're maintaining good condition under the center line, if we're raising the permafrost level, the airstrip would be stable forever. That didn't quite happen. It's very important to take into consideration side effects of embankment, so you need to consider the geometry of the embankment. So minimum, if you want to do 1D analysis, you need to do it at 2 points, center and shoulder. So that's because most of the problem will be initiated near the shoulder, so you need to understand what's going on there, but you need, of course, to know what's going on underneath the center where the load is going to be supported. The ideal, of course, is to do a 2D analysis. It could be half a section if the embankment is symmetric, or full cross section if it's not. Embankment that would build a cross slope, for instance, would be not symmetric. So you need to look at the full section. For new project, thermal modeling is a very good way to assess the problem. So because of course you don't have any information on the behavior of the embankment since it's not built, so you have to assume a few design things, and then do the modeling of the thermal performance of the embankment based on your knowledge of the site. And when you have an existing embankment, the best thing is to combine thermal modeling and temperature measurement at the site. Again, any temperature measurement that's available is going to be useful to build a good model. So it's very important to consider thermal modeling and temperature measurement for as long as possible, ideally a full year on the embankment, if possible, multiple year, but if not, a few days, few weeks, few months will be helpful in calibrating the model. So to make sure that the system is stable, there's 3 ways to look at the problem. The traditional way is to consider raising the permafrost level. So if you look at the system, you have your embankment, you have the active layer, and you have the top part of the permafrost, which is often the ice-rich part of the permafrost, for all sorts of good scientific reason. So the principle is that we need to avoid that permafrost degrade beyond that point during the service life of the structure. So one way to do that is to raise the permafrost underneath the embankment, and that provides a buffer for thermal degradation during the service life of the structure. So degradation occurs in the old active layer and not in the top of permafrost. So again, that has been done very widely in the past. It's still done. It's a good approach, but doesn't assure stability of the system. Another way to look at the problem is to control the thermal regime. So thermal regime can be controlled looking at the average annual gradient between permafrost at the elevation of 0 annual amplitude. So that's permafrost temperature and interface temperature. And if you keep a gradient with the following that general slope at controlling the temperature at that point, you should have a stable system, because this gradient is what it takes to extract all the heat from the ground, and considering all the ground thermal exchange phenomena. So that's one way to look at the problem. And another way is to look at the heat budget at the interface. So there, in that case, the idea is to make sure that the heat budget at that point, so the summation of all the flux going out and the flux going in is equal to 0 or is negative. If it's negative, that means that there's more heat flowing out than there's heat flowing in. So the system is necessarily stable and potentially cooling. So by using that also, it's a very good reference to do thermal design. Give you an example of the strategy based on the thermal gradient and also the heat budget. So if you look at an embankment and you superpose a temperature depth figure on top of that embankment, permafrost temperature is there, okay? If you have interface temperature that's colder than 0, you might think, well, you probably raise the permafrost level near to the embankment interface and you probably have some stability, but the permafrost is going to degrade, because if you have a positive gradient here, that means there's more heat going out of the system than there's heat going in. For example, here, this is the situation at the control section at the Beaver Creek test site. And you can see there that the heat budget that has been calculated by Julie Malenfant-Lepage is a positive. There's 5,000 kilojoule per square meter of heat in excess in the system. So there's more heat flowing in the ground than there's heat flowing out. If you can control the condition where the interface temperature is at the same point than the permafrost temperature, then you have a stable system. And again, that situation is observed at the Beaver Creek test site at the Albedo surface treatment site section, where you have a null heat budget, meaning that the system, there's as much heat flowing out as the heat flowing in, so the system is relatively stable. If you're designing for long term, you need to add some safety factor, safety margin to the system. So you'll aim for a cooler temperature there than the permafrost to allow for the effect of climate change with time. And in that case, you'd get like you see for those two sections that are section where you have ACE layer, air convection layer in the embankment, you have negative heat balance. So very stable embankments. So that can be, that principle can be used using a simplified approach, which is called the ITC approach. ITC means that you're actually using the interface temperature correction. So you need to go from that temperature to this temperature to assure long-term performance of your system. So the ITC becomes an index that is correlated with some geometric parameter of the embankment. So you can adapt the embankment to correct the temperature on the interface. So that's currently there's systems that have been proposed to use that to design the slope and design the surface albedo based on the ITC. So ITC can be used to modify relevant parameter based on empirical relationship. You can also use the heat budget approach, and that's a more rigorous approach. The problem, because then you calculate the heat budget of a non-protected embankment. And if the heat budget is positive, then you need to, you know how much heat you need to extract to make it stable. So stabilization technique would then be designed based on the extraction capacity of each technique. So example of the heat budget, Shangbing Kong has been proposing design chart to determine the heat balance for a given embankment. So that can be done for considering a thermal gradient using the temperature at the interface, temperature permafrost, and the difference of elevation, you get the gradient. And from using the gradient and the plan thickness of the embankment, you can determine the amount of heat, the heat budget. So if, for example, if you're considering 0.1 degrees Celsius gradient, and that's a 4 meter thick embankment, you get a heat balance around 3 million joules per square meter. So again, something that you need to extract to make the system stable. Okay, we'll come back to some techniques to do that, but just want to say a few words about mechanical stability. Mechanical stability, of course, the design of embankment is first of all controlled by requirements for vertical and horizontal curves. So there's design requirements that you can allow for, again, vertical and horizontal curve, and that will dictate the amount of fill that you need to put in a given area. And of course, also this is done by trying to minimize the volume of burrow. So whatever is excavated is used in the fill section. So this is important, of course, for cost and environmental footprint. So based on that, you come up with a thickness. Of course, as we can see, thickness has a major impact on thermal stability. And if a given thickness is going to lead to instability, it's relatively easy to consider increasing the thickness to avoid the problem. But if you, for all sorts of reasons, end up having a thick embankment, you have to be aware that you're going to compress the soil and probably cause some deformation. And you can also induce creeping in the ground, and possibly also instability, like failure into the ground. And that needs to be assessed based on your tolerance to surface distortion. So again, here you have this is a funny figure because it includes actually pressure and temperature on the same axis. But if you increase the pressure, you will decrease the volume. This is volume ratio here, so decrease the volume. And if thawing occurs, you'll get thaw settlement. So this is again the combined effect of temperature increase and stress increase, which can lead to significant change in volume. Also, as an example here, the effect on creep. These are the result of creep test on a glacial till. And you can see that going from a 2 meter thick embankment here, this is based on 40 kilonewton per square meter applied on the ground, to a 7.5 meter thick embankment, you will increase by a factor of 5 the creep rate of your soil. And by going from -3 to -0.5, you'll increase by a much higher factor the creep rate of the ground. Just to give you an idea, in this specific case where you have the 7.5 meter thick embankment over permafrost at -0.5, you can get up to 4% of settlement per year. That means that if you have 1 meter, for each meter of soil affected, you have 4 centimeters per year of settlement. So over the design life of the embankment, you get probably somewhere around 80 centimeters of settlement. This is an example of what can happen if soil creeps under the embankment. So pretty severe settlement occurring under that thick embankment in the Yukon. Of course, you got to be also aware that there might be some stability issue, and that problem can be exacerbated by degradation of permafrost at the toe of the embankment, causing like a thawed soft zone. So there can be shear plane occurring in that zone, causing embankment failure. So that's also something that need to be calculated. There's software that allows you to do that. This is just an empirical equation that allows you to assess if there's potentially a problem. if the height that you calculate based on shear strength of your soil is lower than the projected embankment, you need to do a detailed assessment using a software to calculate the factor of safety. That's an example here that analysis was done for the Povaniktuk airstrip embankment and led to the construction of a berm to avoid the risk of failure at the toe of the embankment. Geometry can be adapted to cope with different type of problem. The idea when you're adjusting the geometry is you have to keep in mind that you need to protect the structural core of the embankment. So the structural core is the zone that supports the load, and that need to be structurally sound. The side of your embankment, the shoulder of the embankment, will assure mechanical confinement and also mitigate environmental effect. So since there's lots of problem occurring near the shoulder of the embankment, there might be good reason to have a wider zone to avoid the problem to affect the structural core. You can also consider a gentle slope that have several advantages. First of all, it provides some good mechanical stability to the core. It reduces the risk of creep failure or shear failure of the ground. And also it reduces the effect of snow accumulation caused by wind blowing. Well, you know. Berms can also be used, again, for the same reason, appear to be effective, but probably not as much as a gentle slope. So two examples of that, the berms that are built along the Alaska Highway in Yukon, and gentle slope here built along the Tasiuak runway in Nunavik. So modifying embankment geometry has some good advantage, but it also involves higher construction costs and larger footprint, higher environmental impact, because you're, of course, building larger embankments using more granola material, but it improves the mechanical stability, provides effective confinement for the structural core, and also improves the thermal stability by reducing snow accumulation. And something I didn't mention, it's also moving water accumulation away from the core of the embankment, which is also something that helps for thermal stability. Quick words about mitigation. If you want to stabilize the system, there's three general approaches to the problem. You can act in the summer, so you can try to reduce heat intake in the summer. By doing that, what you'll do, if you look at the thermal regime and the condition of the permafrost you're trying to protect, this will be acting on the summer swing of the trumpet. So what you do is actually you're pushing in that side of the trumpet curve, and you have a translation of the trumpet towards the left, and typically a raise at the permafrost level. So that can be done by, again, reducing heat intake in the summer. You can also act in the winter. So using the winter swing, this is when you have a strong gradient, so you can effectively pull heat out of the ground during that time. So if you activate heat extraction, what you'll do is you'll have the same effect by pulling the winter swing to the left, and again, translating the curve to the left and raising the permafrost level. And also you can reinforce to face permafrost degradation, as we discussed earlier. So to reduce heat intake during summer, there's thermal insulation, high albedo surfacing materials, and sun shed that are available to do that. So insulation will strongly reduce heat intake in the summer, but we have to keep in mind that it will also reduce heat extraction in the winter. So at the end, the heat budget will be essentially the same near at the interface. But what it does is strongly reduce heat loss. It's essentially strangle the trumpet curve at the level of the of the insulation layer. So it's good. It's a good strategy because it does raise it does stabilize the permafrost. It doesn't really raise the level at the interface unless you put the insulation higher in the system, excuse me. One thing to keep in mind is the entrepreneurs and contracting firm that are told to put insulation in the ground will they will usually plan to do that late in the summer because it's easier to excavate and put the insulation in the summer. But if you do that, you will actually trap warm condition under the insulation layer and possibly thawed ground underneath the insulation layer. And the latent heat that's going to be contained in that thawed ground is never going to escape the system, and you're going to end up with something messy. So insulation needs to be placed in the winter when you're in cold condition to avoid that problem. Albedo surfacing material, something that has been tested in the 60s, as it shows by these guys on the picture. That is in Fairbanks in Alaska, and that's the American Army doing testing on surfacing material for airstrip in the Cold War time. And that experiment, you can see here actually the same section 35 years later, and see the painted section here is still almost intact except for cracks and the chip a little bit painting, but it has been very stable for 35 years while the unpainted section here is a swamp. So anyway, this is a very effective system and is actually led to the painting of the Truly airstrip in Greenland. And it has been stable since construction because of that. Now recently it has been reconstructed using insulation to replace white painting because of the problem of the painting, which is takes lots of maintenance and is also slippery. Nowadays we have new materials, and among those materials we have synthetic bitumen that can be colored. So you can actually produce asphalt with different colors. This is the asphalt that was placed in Dawson City to protect permafrost, and also to make sure that they keep the appearance of the gravel surface road, which was important for Park Canada. So anyway, this technique can be used now. So it's maintenance-free asphalt, very effective in keeping the surface cold. And this is an example here where you can use the ITC, the index I referred to earlier, to design the albedo of a surface for a given context. Sunshed can also be used to protect shoulders. So sunsheds are very effective because they shade the sun radiation during summer, but they also prevent snow from accumulating on the ground, so air can circulate and cool the ground underneath the shed. So very effective technique to protect the slopes, though they are kind of expensive. Example of technique to extract heat during winter: thermal siphon, air convection embankment, heat drain, air duct, snow shed. Again, I'm going to run quickly through them. Thermal siphon, very smart system where you use a liquid that evaporates at low temperature. So by evaporating, the reaction of evaporation is endothermic reaction. So it absorbs a lot of ground heat. So vapor will raise by diffusion in the pipe, reach the condenser where the vapor is going to condensate and release the heat and then flow back down. So this system works without external power in the winter when air is cold and ground is warm, and is extremely effective to remove heat. So you can see here thermal siphon installed on the China Spring Road in Fairbanks, and recently those systems were installed at Dry Creek near on the Alaska Highway in Yukon. ACE, very effective system again, system that allows air circulation. So what happens in the winter when the surface of the layer is cold and the bottom of the layer is warm, the system is unbalanced because the air at the bottom is warm, so it tends to flow up, and the air at the top is cold, so it tends to flow down. So you induce convection cells that are as much as 10 times more effective to extract heat than conduction. So very effective system to cool down in the winter. Examples of application on the Thompson Drive near the University of Alaska and the China, the Kunai Tibetan Highway in China. Again, these techniques have been tested, and Kong has come with a chart to actually determine the amount of heat that can be removed using ACE. And that system can be used for, if you, just to give you an example, this is the heat balance figure that we've seen earlier. So if you look at the 0.2 degrees Celsius per meter thermal gradient and a 3 meter thick embankment, that means that there's 3 million joule in excess in the system. So in order to remove that 3 million joule, you need a 2.5 meter thick embankment to actually extract that, that amount of heat. Heat drain, same principle, using the convection, or in that case, it's an open convection system where air flows in the system, follows a membrane, and is expelled out of the system at the other end. So this is the membrane used for the heat drain. So it allows airflow in the system. An example of application of the heat drain at the Tasiak airstrip and at the Beaver Creek test site in the Yukon. That's a full width application. This is applied in the shoulder. And in order to have the system to work, you need chimney to let the air in the system and the air out of the system at the top. So it actually generates a air circulation in the shoulder, cooling the shoulder. When air ducts can be used also to cool in the winter, air ducts used across the embankment that's been used in China, and longitudinal duct with chimney used in Alaska and on the Alaska Highway. So these are the Chinese ducts going across the embankment that are closed in the summer and open in the winter to allow heat extraction. And these are the ducts used in the Beaver Creek test site in Yukon, where the air goes in, flows along the shoulder, and then is expelled through the outlet here. So actually this is connected to this one here. So it goes in, flows along the embankment, and the hot air is expelled on top. Reinforcement, briefly, I've already talked about that, but the reinforcements is either using, like the old way to reinforce was to use logs at the bottom of the embankment. Modern way to do that is to use geotextile to mitigate movements and avoid local collapse, for instance, on top of an ice wedge. Example here of use of grids on the Alaska Highway to reinforce the embankment and minimize embankment spreading. So in conclusion, just a couple of concluding remarks. Permafrost engineering needs to be based on a very good knowledge and understanding on the context of a project and on permafrost science. Design solutions also need to be developed based on sound thermal and mechanical principle, considering climate change over the design life of a structure. And that means that effective cooperation between permafrost scientists and permafrost engineers is absolutely required so we can actually develop and maintain sustainable permafrost sustainable infrastructure in the permafrost environment. Okay, thank you very much. Merci. I'm open for discussion and question if needed.
Awesome. Thank you very much, Dr. Doré. That was very interesting, and there's a lot of really good information. I know I personally, as a permafrost scientist, learned a lot from that, and we'll definitely be able to take that into future studies. So I saw that someone raised their hand, but maybe put it back down. We have a question in the Q&A from Lorene, and she says that I see the use of polystyrene insulation increasing, but I'm concerned about the long-term consequences of using this material, specifically thinking about repairs, replacement, or removal of the infrastructure. And they're wondering if anyone has considered or invented a more environmentally friendly material that serves the same purpose.
Okay, while polystyrene has been used for several decades in seasonal frost environment, it has been used in Alaska for also several decades in permafrost environment. It is proved to be extremely durable, extremely robust. It works. Again, the key point is you have to install insulation in cold condition, not in warm condition. If eventually you need to excavate the embankment and do something else, of course, you're going to be stuck with something that's difficult to get rid of. You're going to have a contaminated granular material. It's going to be very difficult to extract the polystyrene sheet without breaking them and mixing them with the gravel. And I agree, it could be a mess. There's perhaps a way to take care of that. In terms of using more durable, again, this material has proven to be very effective. I know there's new materials that are becoming available. One of them is cellular glass. It's actually foamed glass that is extremely effective, and it's a normal, like it can be used. Like one of the problem with insulation, as you've seen on the picture, is you need to manually place down the boards. And you can imagine if you're working in the north where it's often very windy, it's extremely difficult, can be costly, can be labor intensive, there's all sorts of problems. The good thing about cellular glass, and there's also equivalent material like the expanded clay, for instance, can be used as a granular material. So you can put that in a layer in the system. And you can even design your system to be big enough, so the granular material are big enough to generate convection. So that will add some efficiency in the winter using convection. And in the summer, it's going to be a very good insulation layer. So you can have a material that will work both in the winter and in the summer. But there's not yet any experiment using cellular glass or expanded clay in permafrost environment, to my knowledge.
Awesome, thank you very much. So the next question we have is, in your design flowchart, what would you describe as low, moderate, and high excess ice content, roughly?
I'm currently working on that decision-making chart, and I've put some numbers, and the numbers are based on the experience. If you're looking, for instance, in the Andersland and Ladany's book, there's a chart where you can see the water content and the settlement, and that's based on the hundreds of tests that have been done in the Mackenzie Valley. The problem with that is it's mostly silt that you have that reflects the behavior of silt. So there's nothing similar for glacial till that would be ice rich, for instance, or things like that. But essentially, what you see is that between 20 and starting at 20% water content, so that's gravimetric water content, you start having some settlement. But between 20 and 30, it's really modest settlement. Between 30 and 40, it begins to be more significant, and not sure exactly we should draw the line at 40 or 50, and anything above that 40 or 50 would be high ice content in terms of based on gravimetric water content measured on the sample, as long as you're recuperating a full undisturbed sample and you're melting the sample and testing the moisture content. So yeah, that would be my range, but other people might have different values than me.
Perfect, thank you. And thank you for the good question as well. So you have a question from Terry Brooks, and they're saying, I can see some cases where we have probably been guilty of oversized embankments with the thought of protecting the permafrost. And they're wondering if you can recommend a permafrost construction manual that deals with the issue of embankment creep due to excessive embankment thickness.
I'm not aware of a manual that gives the recipe to design an embankment for creep. There's probably the best reference would be Anderson and Ladany. They actually discuss a lot creeping of frozen ground, and they have equations to actually model creeping. The chart that I've shown where there is multiple line was done by fitting the model that was proposed in that book, and then you get a full picture. And the rest of it is a question of tolerance. Okay, I've shown an example where if you had a 7 meter thick embankment on ice-rich soil with temperature of -0.5, you'd get probably somewhere around 80 centimeter to 1 meter of settlement over a year over the design life of the structure. Well, that can perhaps be managed. So if you have a gravel road, you can every 10 years you can go fill a little bit, fix the dip, and it will continue. But you can manage that. If you have an airstrip, you cannot tolerate that kind of settlement, especially if you have a paved structure where it's not very easy to come and remove the asphalt, fix the level, and then repave on top. That's very expensive. And again, an airstrip, you cannot allow a dip in the middle of an airstrip. So it depends on your tolerance. Again, I'm not aware of a design procedure to cope with that, but it's possible to assess the creep characteristic of a soil using lab testing. That's very sophisticated testing. There's not many labs in Canada that can do that, but you can get the creep characteristic of the soil and then project the amount of settlement that's going to occur over time. And again, this is a question of tolerance at that point.
Awesome. So kind of a similar request to ask a question, and also I 100% reflect this question. Do you have a recommended resource for permafrost scientists that's at a similar level of engineering detail as the presentation you gave today? So something that's not like an engineering resource, but rather something that can help serve as a resource or a guide to use as reference.
That has been identified by the Transport Canada as being one of the priority was to develop such a guide. Currently, we don't have much. We have a guide. The TAC guide is probably the best resource for engineering purpose. So the TAC, it's called Design and Management of Transportation Infrastructure on Permafrost or something like that. TAC stands for Transportation Association of Canada. And they do give some guidance, but it's mostly best practice. It's not design procedure. I know Alaska just published a general design and management guide for transportation infrastructure in permafrost. I've not gone thoroughly through the guideline, but it's mostly, again, best practice. There's definitely a need for a reference document or a reference, could be a standard or design guide for design to consider thermal stabilization, consider creep sensitivity, all the aspects you have to look at when you're designing an infrastructure in the north. It's still something that is needed. There's nothing, to my knowledge, in Europe. There's some design code in Russia, but not very easy to access and follow. But they do have something, mostly for buildings. I don't know about roads, but it's limited. It's very limited. Again, probably the best reference for most engineering work is the Understand and Ladany book. It's probably it's called Frozen Ground Engineering. It's probably the best. Again, I would say in Canada, you need to have Understand and Ladany and a tag guide on your shelf. It's the essential reference for now. Hope we're going to come up with something better in the near future.
Great. So I'll just add to that, Lorene, in Dr. Dumais' presentation, at the end of it, he gave a slide that had some recommended readings and resources. And I do believe Frozen Ground Engineering and the TAC Guide were one of them, but you can check that out on the PYRN YouTube page. It's uploaded there and you'll be able to see some of the resources he recommended.
What presentation was that?
Simon Dumais' presentation,
okay.
The one before yours. He recommended some at the end. So we have a few more questions, but I'm gonna ask one more, and then Kumari, you had asked one as well, and I'll just read it out quickly. So Kumari had asked that you mentioned the need to consider permafrost science. What are some of the communication barriers? So Kumari, we're actually doing a panel discussion on that next week. So we're gonna have all of the panelists or the lecturers coming back, and we're going to have this discussion on how permafrost scientists and engineers can work together and work on these communication gaps. So if you're free next Wednesday, we'll be able to answer your question then. But for now, our final question is going to be from Thomas, and they're asking that in your design flowchart, what do you see as the main challenges of designing infrastructure? Is it needing better geological models, like having better spatial coverage, better design strategies, or what else?
All of the above. I think we need to improve all of these. I think the design chart I've shown are something that have been built very rigorously by Shangbing Kong. You probably might be listening now, but he did a very good work in developing those charts. They were developed based on site-specific condition and then generalized to a wide variety of condition and then validated using other sites. So it's, again, very rigorous approach. So I think that they're reliable, but like most of the thing we use in the north, we need validation and refinement. So we need additional tests with those methods and see if they work in all conditions. If they don't work, why do we see that there's a problem? So we need to improve those design charts. We need to improve our design methodology. And there's definitely a big need to better decision-making criteria, tools, management tool, decide when to do something, when to let go. And for instance, the very simple question, should we build and maintain or should we protect permafrost so we don't have to maintain or reduce the maintenance level? So we don't have, one of the key things missing is performance information and cost information. How much does it cost to stabilize? How much does it save in terms of maintenance? Unless we have more detailed information about the cost of maintenance, the cost of using fancy techniques in the north, we cannot make the decision what's the most cost effective. And again, there needs to be improvement with those decision-making tools, and that includes the design charts, So all of these have to be built. I think it's a good start, but we need to keep working on those design tools. I don't know if I answered clearly the question. I'm not sure if I.
Yeah, no, I think that was a very good oversight to the question. Basically, that there's still always work that can be done to improve our understanding of things.
More work needed.
Yes. Well, I think with that, we're going to conclude. We had a really good and amazing overview of cold regions engineering and the strategies to site investigations, and a really good discussion with lots of good questions. So thank you very much, Dr. Doré. It was very insightful, and we'll be looking forward to the discussion next week on how permafrost scientists and engineers can do better at working together and maybe work on identifying some of the gaps in how we can proceed and learn more. So thank you very much, and thank you very much everyone for attending, and we'll look forward to seeing you next week.
Thank you very much.
Thanks. Bye, everyone.
Bye-bye.